All right. Good morning, good evening, everyone. Depends where you are. So welcome to the third preliminary talk session. Let me see. I hope everyone can hear me. This is our overall agenda. And as you can see today, we will mainly talk about the covered applications. Today we have two speakers. So the first one is Professor Greg Olson. So he will talk about this genomic materials design, calculation of phase dynamics. So that is the first talk. It will be delivered by live, right? So Greg is here. So after that, we will, as usual, we will have 15 minutes break, right? So you can go to GatherTown and have chat with your friends there, right? Or you may meet some new friends, make some new friends there. After that, we will have Jim Yoko to deliver the alloy design at Apple. So Jim is actually on vacation right now in Hawaii, I believe. So because of that, we don't want to bother him right now, right? So he records this video to us. I haven't played with that yet, but I believe it will be fun. One reminder for this talk is it will not be recorded. This is the agreement with Apple. So the video will only be played once. Okay, after that, we will get into this Q&A session. So mainly, if you have questions, want to ask Professor Olson, this is the time for you to ask. And as usual, after that, the activity will end with this GatherTown social. All right, so that's pretty much the arrangement for today. Next week will be our last session. So this is what we have planned. We will have Professor Jesse Zhao and Professor Zikui Liu to give the talk, essentially about the next 50 years. We will also have the poster session. So the students who got the best poster awards will be there and discuss with the other attendees. So that's pretty much the arrangement. Okay, so let me stop sharing. So Greg, can you please check if you can share your screen? Let me, yeah, I think you can, right? You are the co-host right now.
Okay, let me give it a try, see if I can put my slides up.
Yeah, by the way, Greg, where are you right now?
Oh, I am broadcasting from Illinois at the moment.
Okay, that's great. Okay, while you are preparing, so let me give a brief introduction. So Professor Greg Olson is currently the Thermocock Professor of the practice in the Department of Material Science and Engineering and MIT. So he's a co-founder of this NIST-supported ChiMat Center. He is also a founder of Questec. He's a member of a National Academy of Engineering, also the Royal Swedish Academy of Engineering Science, and a fellow of ASM and TMS. One surprise to me is he's also a member of American Academy of Arts and Science. So I guess I will check with him on some questions of arts.
Excellent.
Yeah. So he has authored more than 300 publications. So I guess everyone know Greg. He got his BS, MS, and also Science of Doctor from MIT, and now he is back to MIT, right? Start his new career. So today
Yes.
it is our great honor to have Greg to give us the first excellent talk. So Greg, it's all yours.
Okay, I will try to be excellent as best I can. All right, so today, for the topic of applications, I would like to examine the true meaning of CalFAD. It is my job description as thermocalc professor to help restore MIT to a global center of CalFAD technology. And it had been our plan to host this CalFAD 50 Genome 10 conference at MIT. But unfortunately, due to global catastrophe, we'll have to wait a couple years before we host at MIT. We hope you'll join us then. And at that time, we'll use that occasion to pay tribute to the legacy of the late Larry Kaufman as we return the conference to Larry's origins. So we hope you'll join us then. As John Ogren pointed out, the real context of this technology now is what began as the National Materials Genome Initiative announced by President Obama a decade ago, which has really now become a global activity. And the overarching goal of this is to develop the technology that can take what has historically been a 10 to 20 year materials development cycle and compress that by at least 50%. And as John pointed out, the original National Academy study that called for this initiative was back in 2004 on the very topic of accelerating the transition of materials technology. And it looked at the analog of the Human Genome Initiative, acknowledging that it is the nature of the human genome to be an actual physical database that directs the assembly of the dynamic structures of life. And so the concept was an equivalent genome for materials would be the fundamental parameters that direct the assembly of the dynamic microstructures of materials. So that was the concept. Historic milestone in the development of this technology that just predates the MGI initiative was the first flight of aircraft landing gear of Questex Ferrium S53 stainless landing gear steel. It was the first stainless steel to meet the mechanical performance requirements of landing gear, allowing the elimination of toxic cadmium plating. But much more significantly, it was the first fully computationally designed and qualified material to make it all the way to flight. And this really does measure a level of maturity of this technology. And that's reinforced by this timeline. It is clear that the genome we have is the CalFAD system of fundamental phase level data. And while any nucleation event has many precursor fluctuations, if we follow the thread of the evolution of CalFAD, we can trace its origins back to Kaufman and Cohen in 1956 with their analysis of the iron-nickel binary system. But here I'd like to emphasize that particularly in the academic world and the way that we teach thermodynamics, there is a common misconception that thermodynamics is about equilibrium. I think if that were the case, we would have called it thermostatics. Thermodynamics was created to describe the dynamics of heat engines, where equilibrium calculations set useful bounds on the real dynamic problems of interest. And the same is true for the problems we address in materials engineering. It really is the dynamics that we created these tools to deal with. The origin of the CalFAD acronym, Larry came up with it to counter the term FAComp, in which there was a practice of trying to estimate solubility limits from the attributes of a single phase. And of course, Larry wanted to acknowledge that those limits really come from phase competition as expressed by phase diagrams, and hence the CalFAD acronym. But if we look at what Kaufman and Cohen were actually doing with the iron-nickel system, it had nothing to do with calculating phase diagrams. It was taking the information that's in an equilibrium phase diagram and reducing it to its more fundamental underlying thermodynamics, and specifically to treat systems far from equilibrium, in their case, Martensitic transformations. And for that purpose of treating the dynamics of martensite, it was actually Morris Cohen's vision that by having accurate low temperature thermodynamics that appropriately acknowledged the third law curvature of free energies, it would be possible by studying time-dependent low temperature transformation that measuring the dependence of activation energy on driving force would help to understand the actual governing mechanism of martensitic transformations. And that did come to pass over time. And we now have a very predictive theory of martensitic transformations in which that first CalFAD exercise in the 1950s really set the groundwork for that. It was my privilege to start to work with Larry in 1970 when I first joined the group of Morris Cohen. It was clear that Larry was much more an engineer than a scientist, but he was committed to science-based engineering, really very visionary at the time. His company, Man Labs, was a metallurgical consulting company that offered CalFAD services, and to a large extent was really a precursor of what Questec is today. So we have a lot to thank Larry for. With the evolution of CalFAD, it very quickly moved beyond solution thermodynamics to include mobilities to deal with dynamic problems, and has over time expand not only in the scope of the systems it describes, but the various phase level attributes that are described within the framework. But again, it is the control of dynamic systems that really motivate that expansion of those parameters. It was the appearance of ThermoCalc as a commercial software system and supporting database system that really inspired our founding in 1985 of our SRG Design Consortium to build a system of computational materials design intended to be general, but it was first focused on high performance steels, acknowledging this class of materials as the one we had studied the longest and deepest and actually had the highest quality of fundamental data at the time. And I should say that the real function of CalFAD in this context of design is it really allows us to apply the mechanistic fundamental understanding we already possess, but apply it in a system-specific quantitative form and really enable a science-based form of engineering. So our first designs were in steels, which ultimately led to the founding of Questec in the late 90s. But meanwhile, at the university, we had various demonstration projects across different classes of materials using the same methodology. And it was the successes in computational materials design demonstrated in the 90s that really set the foundation, built the case for the DARPA AIM initiative in the early 2000s, which was the start of what we now call ICME. And this was to go beyond the initial design of material to address the full materials development cycle, which is the goal of the Materials Genome Initiative, the linking of microstructural models to macroscopic process simulators to accelerate process optimization at the component level, and very importantly, to simulate manufacturing variation within allowed tolerances to give accurate forecasts of minimum properties that become the design allowables that a material user can depend on. And this was to replace statistical inference with probabilistic science that could greatly reduce the amount of experimentation necessary to get a material all the way to certification. So at this point, we have over 60 years of our fundamental CalFAD system. We've got over 30 years now of a design practice and now 20 years of a full ICME technology, where the cycle compression that this is allowing, as I will get to later in my talk, is really allowing for the first time the expansion of concurrent engineering that used to mean everything but materials to now include materials in that concurrent engineering cycle, with a profound impact on what concurrent engineering can now achieve today. Core of our approach comes from the philosophy of the late Cyril Stanley Smith, who wrote about the intrinsic complexity of multi-scale dynamic materials microstructure, and therefore advocated that we really should take the systems approach that is used in other branches of engineering as the framework to deal with material complexity. In taking that to heart, a core concept was this linearization of the interaction of the four domains of material science of engineering, advocated by Morris Cohen, and which he described as a reciprocity between the opposite philosophies of science and engineering, where the deductive cause and effect logic of predictive science moves from left to right, and the inductive logic of the goal-means relations of engineering moves from right to left. So we've used that as the backbone of a system structure of materials, adding to it Smith's structural hierarchy, so that each design project starts with this kind of system chart, where a performance goal of the material can be mapped to a quantitative set of property objectives, which can relate back to subsystems of hierarchical material structure, which dynamically evolve throughout the sequential stages of processing. And this allows us to identify and prioritize the structure property and process structure links for which we want to build predictive design models. And at this point, we could use empirical interpolative correlations, but in fact, given the power of the fundamental CalFAD databases, our commitment from the start was to use mechanistic models grounded, parameterized to use the fundamental data in CalFAD to be far more predictive than is possible with empirical modeling. This led to a down selection of tools of computational material science to support this kind of engineering that are represented here, where the biggest impact of DFT quantum mechanical methods has been the prediction of interfacial properties. The material science has given us the predictive theory of nanoscale precipitation and associated strengthening. And continuum methods of micromechanics have been applied to the simulation of unit processes of fracture and fatigue. And it's this combination of quantum physics, material science, and continuum mechanics that has given us the capability for performance-driven design. Equally important is the constraint for scale-dependent processability of materials, and that's enabled by the material science models of solid-solid and liquid-solid phase transformations, which are scale-dependent through heat transfer. And taking that into account, using macroscopic process models for the final scale of production of material, it's been possible to constrain a design upfront to be processable at the final scale of production. The software models and their platforms are represented by these acronyms. Equally important is the advanced instrumentation that has allowed us to calibrate and validate these models, and importantly, quantify the uncertainty of our model predictions to incorporate in our design practices. The early research in the 1980s began with the highest performance M2C carbide secondary hardening steel, AF1410, and by a vast combination of experimental techniques, we fully mapped out the evolution of those strengthening carbides. The data validated predictions of the Langer-Schwartz theory of precipitation at high supersaturations, where the system evolves by nucleation and coarsening without supercritical growth. And here the length scale is scaled to the initial critical nucleus size, which in turn scales inversely with the precipitation driving force, giving us a thermodynamic handle on particle size. It was important to acknowledge, though, that the trajectory of composition and associated lattice parameters is consistent with coherent nucleation. So it was necessary to add to the chemical thermodynamics the additional elastic energies of the coherent state. But with those insights, we were able to build out thermodynamic-based approach to strengthening efficiency that's summarized by this derivation here, starting with the Orowan precipitation strengthening contribution and predicting that it should not only scale with phase fraction to the 1/2 power, but actually directly with the magnitude of the precipitation driving force. A series of experimental cobalt nickel steels were made with a fixed carbon content and thereby fixed final phase fraction that validated this prediction. It was important as well to not only treat the elastic energies of coherency, but as well acknowledge that the starting state before alloy carbide precipitation is a state of para-equilibrium with cementite that reduces the carbon potential. But taking that into account, we were able to show that there's this strong enough driving force dependence for the hardness to vary from the Rockwell C40s to the Rockwell C60s. So very strong primary contribution. And this has then given us the thermodynamic handle that has allowed us to design strengthening efficiency so that for a given carbon content, we could get 50% more strength than previous steels. Other major advance very early on in the program was applying the all-electron accurate DFT calculations to the surface thermodynamic interfacial embrittlement to enhance boundary cohesion to offset hydrogen interaction. The framework for that was the Rice-Wong model that predicted embrittlement potency would scale with the energy difference of a solute in the grain boundary and free surface environments. This represents the measured embrittlement potency of phosphorus and sulfur and the cohesion enhancing contributions of boron and carbon, the most well-studied components in steels. And this actually is showing the DFT prediction of those energy differences lining up quite well. So we're able to validate that the predicted thermodynamics and the framework of the Rice-Wong model is capable of describing the embrittlement, and then went on to the much less studied area of the role of the substitutional alloying elements. And this began with the red points predicting this energy difference for manganese, molybdenum, and palladium. We then use that as calibration points for a data mining exercise that mapped these quantities back to handbook values of atomic size and individual cohesive energies and other thermodynamic parameters to make the prediction that's shown by the black points here. This allowed us to identify the most potent cohesion enhancers. And then this was followed by the rigorous calculations shown in blue that validated that the simplified model had helped us identify the most potent cohesion enhancers. We find that while the rigorous calculations have an accuracy within 1/10 of an EV, the simplified model was within 0.2 EV, which is more than enough to confidently predict the greater than 1 EV potent cohesion enhancers. And this type of database was used to then design grain boundary composition in our high performance steels. And we have succeeded in these very high strength landing gear steels, completely eliminating the intergranular form of stress corrosion cracking as a result of this enhanced boundary cohesion. So that's one example of a surface thermodynamic genome that's coming entirely from the DFT calculations. The actual parametric design is performed graphically as represented here. This is in the example of the stainless landing gear steel, where we're looking here at a pair of composition variables, starting with optimizing the nanoscale structure that is produced in the final stage of processing. This is looking at the combination of the thermodynamic driving force plus phase fraction to predict the composition range that meets our strength requirements. Overlaid on that are the processability constraints of the MS temperature to get a fully martensitic structure, as well as contours of the solution temperature necessary to put those components in solution during austenitizing. With that optimized, we back up to earlier stages of processing, and this is an optimization of the MX phase grain refiners with a composition and processing temperature variable shown. So we're constraining these carbides to be soluble at homogenization temperatures, able to precipitate in fine form at hot working temperatures, and maintaining a necessary grain pinning phase fraction at the final austenitizing temperature. And similarly, we can back up to earlier stages to define the deoxidants and sulfur gettering compounds that ultimately become the primary inclusions. Doing this graphically also gives us a sense of the sensitivities that allow us to take robust design strategies. The first four commercial products to come out of this are a pair of high-performance carburizing gear steels that are now being qualified for helicopter applications, and we now have two flight-qualified aircraft landing gear steels. All four of those designs use this thermodynamics-based optimization of strengthening efficiency that brings the carbide size down to an optimum 3 nanometers as validated by this early 3D atom probe reconstruction. And that efficiency of strengthening, allowing us to get to the desired strength with less carbon, is really helping us to better manage the trade-off with other properties such as fracture toughness or corrosion resistance, allowing each of these steels to be best in class. The AIM project is where we first coupled our microstructure models to macroscopic process models in the context of process optimization of a nickel-based superalloy turbine disc. And for this, we initially built the Precipicalc simulator using a mean field approximation, but grounded in the CalFad system, which has now become the commercial product TC Prisma. But that was the necessary tool to meet the goals of the DARPA AIM project, and that was then integrated through the eyesight integrator with the other tools of macroscopic engineering. And first, it was then used to couple to heat transfer simulations and predict the spatial distribution of microstructure and strength in a turbine disc. Which was then applied to the process optimization in a subscale disk that was whose performance was validated by overspin burst testing. And then we went on to the most challenging problem, which is Monte Carlo simulation of manufacturing variation within the tolerances of composition and processing to get the shape of the final distribution of strength at room temperature and elevated temperatures. And we demonstrated the ability that compared to statistical inference, that in this case was 700 turbine disks being measured to pin down a 1% minimum property, we demonstrated that by accurately predicting the shape of the distribution, we could then calibrate by linear transformation to as few as 15 data points to accurately predict that 1% minimum property within 1 KSI. And that methodology then proven in the case of the turbine discs was then applied to our landing gear steels, which were the first examples of the application of this methodology to accelerate the qualification of a new alloy. Follow on to that was a 4-year project supported by NASA Glenn to go back over the AIM methodology and develop the protocols to manage uncertainty within this framework. And this was done in the context of process optimization for dual microstructure heat treatment of 3rd generation disc alloys. So for each of those new alloys, we first brought them to equilibrium and compared the predictions of the gamma prime compositions and fractions at equilibrium to down select the most accurate database available. And if necessary, to get the exact phase fraction, we would apply a rigid energy shift in the GES module of thermocalc to get very accurate phase fractions. After pinning down the thermodynamics, we would then run diffusion couples against pure nickel and compare the mobility databases, and if necessary, apply a uniform scaling factor to the diffusivity matrix to get high accuracy in our diffusivity predictions. And then with those pinned, we came up with a simple quenched pin experiment to measure the nucleation undercooling to define the coherent elastic energy. With that calibrated, we made predictions of the type of slow cooling experiment that would drive the system entirely into supercritical growth so that we could, for the larger particles, get the intercoherent interfacial energy, but very significantly also establish the interfacial mobility prefactor for the growth of incoherent primary particles. And then the final was the fine tuning of molar volume databases to predict misfit and the corresponding critical size for coherency transition. So in this way, we were able to get very high accuracy predictions throughout complex heat treatment. And this was actually then used by Rolls-Royce Indianapolis in the process optimization of their RR1000 dual microstructure heat-treated turbine disc. That's had an important impact on the actual design with uncertainty practices that we've then established. It was actually in the late 90s that Haumet called to our attention the problem of trying to scale up single crystal turbine blade alloys from the aeroturbine scale to the very large scale of industrial gas turbines. And the problem here is the macro segregation defects, so-called freckles, that are driven by thermosolute convection. The physics of the problem was already well established in the late 90s. We took a look at the ability to predict the critical Rayleigh number for this by predicting the solid liquid partitioning during solidification and the associated liquid molar volumes in order to predict the buoyancy that would drive this process. And it was clear in the late 90s, CalFed wasn't ready. Our databases did not have the accuracy to control those parameters. Fortunately, 15 years later, we got the opportunity at Questec to come back to this problem under DOE support. And we took that multi-database strategy, found the best database for each attribute, and found that now we could not only constrain the partitioning, the buoyancy of the liquid to be processable, but as well, we were able to use the multi-component thermodynamics to more efficiently partition rhenium between gamma prime and gamma and make more efficient use of it. And then this resulted in a one rhenium single crystal alloy that had the processability of a rhenium-free alloy and could go all the way to IGT scale, as demonstrated in collaboration with Siemens. But by the efficient rhenium partitioning, this one rhenium alloy could give us the creep performance of a three rhenium alloy. So it really was a victory for the use of uncertainty management within this CalFed framework to solve a very complex, sophisticated problem. Context of our ongoing university research now is the TriMed Center for Hierarchical Materials Design that really functions as the lead research center of the MGI. It's now in its second 5 years of its 10-year plan. Within this center, I lead a subgroup on the design of new alloys for additive manufacturing. And this is something that, starting with the DARPA Open Manufacturing Program, Questec at this point has had over 60 projects of, and this is a summary of some of the early projects, that is not only looking at the design of the new alloys that can get more value out of additive manufacturing processes, but also look at the adaptation of the A methodology so that we can very efficiently predict location-specific minimum properties in printed components to accelerate their qualification. So along the way, to constrain materials for resistance to cracking during printing, we have developed a combined cracking resistance parameter that combines the parameter that has been developed by the casting industry for resistance to hot tearing, and combine that with the freezing range, which comes from the welding technology to constrain against welding fracture. And that combined parameter has then allowed us to constrain compositions against those cracking mechanisms. As well, there is another criterion on the quench suppressibility of precipitation strengthening in these alloys. So that's given us the constraints to design specifically for the process. And then there's the matter of actually exploiting the unique characteristics of printing, particular laser fusion processes, where we combine boiling melts with very rapid solidification. And our best example of designing for that to achieve microstructures that could not be achieved by wrought processing is a L12 strengthened high temperature aluminum, where in this case, as shown by the equilibrium step diagram here, in the ground state structure, we exploit an aluminum nickel eutectic for the hot tearing resistance and get a dispersion of multi-component L12 phase. Not shown in the equilibrium diagram is another very important constraint, that under non-equilibrium Scheil solidification, the system will tend to form a metastable ternary phase, which becomes the reservoir for the rare earth elements in this system, which then by rapid solidification is finally dispersed. And then that allows us to support the precipitation at an even finer scale of the L12 precipitates. And this has allowed us to maintain high strength at high temperatures, outperforming the scandium-bearing scalmalloy with a scandium-free L12 with good strength in the region of 250 to 300 degrees C. So really, this is a unique capability enabled by a unique microstructure that we arrive at by making optimal use of the unique process pathway of laser fusion additive manufacturing. I wanted to come back to the original goal of Kaufman and Cohen in using accurate low temperature CalFad thermodynamics to get at the mechanism of martensitic transformations. Actually, though, I think I'm running out of time here, so I think I'll skip over that. But I just wanted to say that Eddie Pang was the coach of a project in our first offering of the computational materials design class at MIT. And this really helped redirect his thesis towards CalFad-based design. And in graduation just a couple of weeks ago, Eddie received the Best Doctoral Thesis Award in the Materials Department based on that work. This is the time card for the acceleration of the qualification of our two landing gear steels. The second landing gear steel did make it in about 7 years, but this was the subject of a NIST study for the MGI that looked at both the technology accelerators and the inhibitors and doing this within a small business environment, and concluded the technology demonstrated, if it had continuous funding of the project, would be capable of 3-year cycle. And that really is important to finally enabling the concept of concurrent engineering. And the first historic example of that was the 4 alloys of the Apple Watch. We'll hear more about that from Jim Yurko's talk. that was designed concurrently with the device and delivered in under 2 years from acquiring the CalFad-based technology that enabled it. And this then transitioned in 2015 to my former student and founding Questec president, Charlie Kumin, after 3 years at Apple, moving to become vice president of materials technology at both SpaceX and Tesla, reporting directly to Elon Musk. This was followed a couple of designs of alloys by Questec for SpaceX, which we can't really talk about unless there's a tweet. And fortunately, there is. In the end of 2018, Mr. Musk put out this tweet about the burn-resistant nickel superalloy that Questec designed and SpaceX developed. That really is the central enabler of the concept of the Raptor engine for the Mars Starship, that's enabling the very high oxygen pressures that allow its efficiency. And recently, Charlie Kumin gave a lecture on how they have taken the standard target cascade and validation system of concurrent engineering and fully collapsed it into total concurrency that has very significantly been allowed by the integration of materials at an early stage into the concurrency process, taking advantage of the intrinsic reliability and predictability of a truly designed material. So it really is a new concurrency. And very recently, it was Mr. Musk's vision that he wanted to be able to build an aluminum car, build its structure in 2 parts by scaling up die casting. Charlie told me about this aspiration, and I was amazed that within only 2 years, they had not only designed the new alloys that could allow die casting to move to this scale, but they had already built the pilot plant, and they now have plants all around the world that are scaling this up. This could well be the greatest innovation in lightweight automotive technology to build cars by this kind of high scale die casting. The most recent development, it was just announced recently that Mr. Musk is a strong enough believer in this new technology that in addition to the 2 materials groups that Charlie has at the 2 companies, they have now produced a new group at Tesla, that is the materials applications team, to accelerate the adoption of these design materials. And Mr. Musk no longer wants to use the legacy alloys of empirical development. He wants all his materials designed so they're better and more reliable. So I think at this point, Elon Musk has become the most likely influential advocate for CalFad-based materials technology. It's a great thing to see. So finally, I would like to say that if we look back to its origins and its future, the true meaning of CalFad is calculated phase dynamics. And I think at that point, I'm almost on schedule.
Mm-hmm. All right, okay, that is great. Yeah, as I say, right, this is an excellent talk. All right, thank you very much.
I met the bar in excellence, thank you, okay.
Yeah. So I already saw some people adding a question there in the Q&A session, but if you have questions, you can type in this Q&A that button there. You keep that, you click that, add your question there. But please hold for that. We will have a 15 minutes break in gather time. And after that, we will play the second video. And after that, we will officially get into this Q&A session. So,
okay, so I should return then for the question and answer period.
Yeah, so
I will do that.
Also go to the gather time. I believe you will have fun there.
I'll see if I can find it. Okay.
Yeah. All right. Okay. That's great. Yeah. Thank you very much, Greg. Yeah.
All right. Welcome.
All right. Thank you, everyone. Yeah.